everyone, my name is Katie, and I'm here to teach you about black holes today. I chose this topic because I find them interesting. There's a lot of misconceptions about black holes, and even today, scientists still argue over the facts surrounding black holes. So in my presentation, I will be answering questions such as, what is a black hole? How are black holes formed? Can you destroy a black hole? And how would they affect you? Over 2 centuries ago, the English geologist John Michell realized that it would theoretically be possible for gravity to be so overwhelmingly strong that nothing, not even light, could escape its gravitational pull. He called these regions dark stars. He explained that in order to generate such gravity, an object would have to be very massive and unimaginably dense. At the time, the necessary conditions for these dark stars seemed physically impossible, and black holes were dismissed as science fiction. In 1916, the concept was revived when German astrophysicist Karl Schwarzschild decided to compute the gravitational field of stars using Einstein's new field equation. Schwarzschild limited the complexity of this problem by assuming the star was perfectly spherical, gravitationally collapsed, and did not rotate. His calculations yielded a solution aptly called the Schwarzschild singularity. A black hole, by definition, is a region of space that has a gravitational field so intense that no matter or radiation can escape it. There are 2 major components of a black hole: the event horizon and singularity. The event horizon is not a physical place that is made of matter. It is a theoretical boundary around the black hole where no light or other radiation can escape beyond it. At this boundary is where the escape velocity is greater than the speed of light. Therefore, nothing can escape the black hole's gravitational pull, and basically there is no coming back after crossing the event horizon. At the center of the black hole lies the singularity, where matter is crushed into infinite density. The pull of gravity is infinitely strong, and space-time has infinite curvature. To better understand space-time, think of space as like an object, like a sheet of fabric. What we perceive as gravity is really just a warping of space, similar to the way a bowling ball on a bed would warp the shape of the mattress. The more massive an object is, the deeper it will sink and warp space. Therefore, singularity is the point where there is zero volume but infinite density. Inside a star, gravity tries to pull everything closer together. But at the same time, energy released by nuclear reactions heats the stellar interior. The pressure of the hot gas pushes out so that gravity and pressure balance exactly. When a massive star runs out of nuclear fuel, an unstable situation develops. Gravity gets the upper hand. The outer layer explodes in a supernova and the center region implodes. If the central core of the star is massive enough, such as 10 times the mass of the Sun, nothing can stop its collapse and it becomes a black hole. The mass of a star ultimately decides the outcome when it dies. Black holes are created when very massive stars die. We can see that when our sun dies, it would become a white dwarf. This is because it is not massive enough to compress itself to the point of singularity. However, using Carl Schwarzschild's equation for black holes, the Schwarzschild radius, he explains that anything compressed enough can technically become a black hole. So what if the sun were to be compressed enough to become a black hole? Black holes are often given a negative stereotype, saying they're like vacuums in the universe that suck up anything and everything that dares to go near them. This is not necessarily true. Although the gravitational force is very strong in black holes, they're really only dangerous if you come too close to one, which is similar to any massive object in the universe. To elaborate on this, if the sun were to become a black hole, the surrounding planets would orbit around the black hole just as they do now with the sun. Also, if an object were to get too close to the sun, it'd be pulled into the sun's gravitational field, just as an object near a black hole would get pulled into its gravitational field. What is unique about black holes is that since there is such a drastic change in gravity, if you were to fall into a black hole feet first, there would be a point where the force of gravity on your feet would be significantly stronger than the force of gravity on your head. The difference in gravity from head to toe usually goes unnoticed, like when you're standing on Earth, but since the gravitational pull in a black hole is so intense, the force of gravity on your feet could be billions of times stronger than the force of gravity on your head. This basically stretches your body into a noodle shape, and the process is actually called spaghettification.
I'm slipping, Bender! The pull is too strong!
I can't live without you. If you let go, I let go.
No! You have too much to live for. It may hurt for a while, but one day you'll share your love again. After all, it's shareware.
Don't talk like that. Tragic romances always have a happy ending.
Farewell!
No! She's gone.
But she saved all our lives. Without her, we're light enough to get away.
Don't cry, Bender. Nobody really knows what happens in a black hole. It's possible she's still alive in another dimension somewhere. Right, Professor? Oh, yes, absolutely. Not a chance.
There are different types of black holes. I will discuss 3 different types: stellar black holes, supermassive black holes, and miniature black holes. The type of black hole being created depends on its mass. Stellar black holes, or stellar mass black holes, are created during the life cycle of a massive star. After the supernova, if the core is less than 2 to 3 solar masses, the star becomes a neutron star. But if the mass is greater than 2 to 3 solar masses, then the pressure of the neutrons is unable to stop the collapse and a stellar black hole is formed. Since radiation cannot escape the extreme gravitational pull of a black hole once it crosses over the event horizon, it is difficult to discover one in isolation. Stellar black holes are therefore most easily found in X-ray binary systems, where gas from a companion star is being pulled into the black hole. It is a misconception that black holes are the darkest, blackest things in the universe, because they can also be the brightest. As black holes pull matter into them, the matter circles around like a drain in your bathtub. The ring of gases circling around the black hole is called an accretion disk. As gases circle around before crossing the event horizon, the gas is heated and emits a very bright light. They can be the brightest objects in the universe. You can also detect a black hole by observing the distortion of light from sources behind a black hole. Supermassive black holes contain between 1 million to 1 billion times more mass than a typical stellar mass black hole. Most supermassive black holes are too far away to be observed. However, there are a handful of confirmed supermassive black holes. Supermassive black holes are thought to exist at the center of most large galaxies, including our own galaxy. Sagittarius A is a supermassive black hole located in the center of the Milky Way galaxy. Sagittarius A is approximately 44 million kilometers across, which is about the same distance from Mercury to the Sun. Astronomers have estimated that it contains 4.31 million solar masses. astronomers have not actually seen the supermassive black hole itself. Instead, they have observed the motion of stars in the vicinity of Sagittarius A. After 10 years of observations, astronomers detected the motion of stars that came within 17 light-hours distance from the supermassive black hole. That's only 3 times the distance from the Sun to Pluto. They concluded that only a compact object with the mass of millions of stars would be able to make a high-mass object, like a star, move in that trajectory. Miniature black holes have actually never been proven to exist. However, theory suggests that these miniature black holes might have formed in the early universe. Miniature black holes have event horizons as small as the width of an atomic particle and contain as much matter as Mount Everest. Scientists believe that these miniature black holes could have been created during the Big Bang. Between 10 to 20 billion years ago, all matter and energy was compressed into a single point. Then this tiny point exploded and expanded rapidly. Some parts may have expanded more rapidly than others, compressing some matter and squeezing it into miniature black holes. When humans starve, they grow thin and eventually die. When a black hole starves, it too grows thin and dies, but it does so in a very spectacular way, in a burst of Hawking radiation. In 1974, Stephen Hawking showed that black holes should emit electronic radiation with a black body spectrum. This process is also called black hole evaporation. In brief, this theoretical process works like this. Particle-antiparticle pairs are constantly being produced and rapidly disappearing. These pairs are virtual pairs, and their existence is a certain consequence of the uncertainty principle. However, if one such virtual pair pops into existence near the event horizon of a black hole, one may cross it while the other escapes, and the black hole thus loses mass. A long way away from the event horizon, this just looks like black body radiation. It turns out the smaller the mass a black hole has, the faster it will lose mass due to Hawking radiation. Right at the end, a black hole disappears in an intense burst of gamma radiation. This is because the black hole's temperature rises as it gets smaller. Thank you so much for watching my presentation. I hope you enjoyed it, and I look forward to watching your videos as well.